Thanks to my Patreon members for supporting this channel. You can support this channel by going to my Patreon page. Link is in the description below. Now back to the video.
Google Deepmind just released a new machine learning paper titled Deliberation in Latent Space via Differentiable Cache Augmentation. In the rapidly advancing domain of artificial intelligence, large language models have emerged as powerful tools capable of generating coherent and contextually rich text. These models are the foundation of numerous applications, from chatbots to advanced problem-solving systems. However, as tasks become more complex, the need arises for these models to think more or engage in intermediate reasoning steps before delivering their responses. Traditionally, this has been achieved through generating and processing discrete sequences of tokens. While effective, this approach has limitations, including significant latency costs and challenges in optimization. A groundbreaking work titled Deliberation in Latent Space via Differentiable Cache Augmentation introduces an innovative solution to these challenges, proposes a paradigm shift by leveraging the latent representation stored in a model's key value, KV cache, using a novel coprocessor to enhance the reasoning capabilities of LMS. To understand the significance of this research, it is crucial to recognize the challenges in enabling intermediate reasoning in LMS. Current approaches often involve generating sequences of discrete intermediate steps or engaging in token-level computations in real time. While these methods improve model performance, they are computationally expensive and difficult to optimize in an end-to-end fashion. Moreover, traditional approaches rely on just-in-time computations, where additional reasoning steps are performed sequentially during the generation process. This dependency on sequential processing not only increases latency, but also imposes strict demands on computational resources, limiting scalability. Question arises: can LMs be augmented to deliberate and refine their reasoning without incurring these limitations? The answer lies in the innovative concept of cache augmentation. The study introduces a unique approach inspired by the emerging field of KV cache compression. Instead of focusing solely on discrete token generation, the researchers propose augmenting the KV cache, a repository of latent embeddings that represent the model's memory during text generation, with additional latent embeddings. These embeddings are generated by an external coprocessor, which operates asynchronously and independently of the frozen base model. This coprocessor leverages standard pre-training data and is trained using the language modeling loss. Importantly, the base transformer model remains unchanged, allowing the coprocessor to operate as an auxiliary component. The process works as follows: cache processing. The LM processes an input sequence and generates a KV cache. Coprocessor intervention. The KV cache, along with all trainable soft tokens, is passed to the coprocessor. Latent embedding generation. The coprocessor generates a set of latent embeddings that augment the original KV cache. Enhanced decoding. The augmented KV cache is used by the base model for subsequent decoding, improving the fidelity of the generated output. This approach introduces several key advantages, including end-to-end differentiability, asynchronous operation, and the ability to enhance reasoning capabilities without modifying the original model architecture. There are a few key advantages of the approach. End-to-end differentiability. Traditional reasoning enhancement techniques often require complex optimization methods such as reinforcement learning, which can be difficult to implement and scale. In contrast, the proposed method enables end-to-end backpropagation during coprocessor training, leveraging the standard language modeling loss. This streamlines the training process and ensures scalability. Asynchronous operation. Since the coprocessor operates offline and asynchronously, it can function independently of the main decoding process. This flexibility allows for strategic deployment of additional computation only when necessary, reducing latency and optimizing resource utilization. Compatibility with existing models. The approach does not require any modifications to the frozen base model, making it compatible with existing LMs. This modularity ensures that the coprocessor can be integrated seamlessly into current workflows without disrupting established systems. Researchers evaluated their method using the Gemma 2 model, a state-of-the-art LM trained on diverse datasets. Their experiments focused on reasoning-intensive tasks such as those found in the YesMake and AMLU benchmarks. The results were striking. On the GSMake benchmark, the BAFA augmented model achieved a 10.05% improvement in performance. On AMLU benchmark, the improvement was 4.7%. Validation perplexity consistently decreased across tasks with larger numbers of latent embeddings, leading to better performance. These findings underscore the potential of cache augmentation to enhance LM capabilities, particularly in tasks requiring complex reasoning. To elucidate the proposed framework, the paper includes several key figures. Figure 1, an architectural overview illustrating the interaction between the frozen LM, the KV cache, and the coprocessor. Figure 2, a detailed depiction of the coprocessor training framework, highlighting the process of multi-position augmentation and ahead token prediction. Figure 3, a comparison of validation perplexity across models with varying numbers of latent embeddings, demonstrating the efficacy of cache augmentation. The introduction of differentiable cache augmentation represents a significant step forward in the field of AI. By enabling LMs to deliberate on their memories and refine their reasoning processes, this approach opens up new possibilities for solving complex problems efficiently. Furthermore, the asynchronous nature of the coprocessor suggests exciting avenues for future research, including scaling to larger models. Applying the coprocessor framework to larger LLMs could yield even greater improvements in high performance. Exploring modular architectures, the use of multiple coprocessors, each specialized for different tasks, could further enhance the versatility of LM's diverse downstream applications. Beyond traditional reasoning tasks, cache augmentation could be applied to areas such as creative writing, code generation, and scientific discovery. In conclusion, deliberation in latent space via differentiable cache augmentation introduces a novel and transformative method for enhancing the capabilities of frozen decoder-only language models by incorporating a learned coprocessor to augment the KV cache. This approach achieves significant improvements in reasoning-intensive tasks while maintaining compatibility with existing architectures. The asynchronous and modular nature of the coprocessor paves the way for a new era of AI research where LLMs can engage in deliberate and computationally intensive reasoning processes. As the field continues to evolve, differentiable cache augmentation is poised to play a central role in advancing the AI capabilities of language models and their applications. Thanks for watching, and I will see you in the next video.